Good morning, everybody. I will do an introduction of what we can do with synchrotron microtomography. It's not an exhaustive presentation because there are plenty of different variations of this technique, so I will focus on the most common one, that is the propagation phase contrast. And for that, I will use the example mostly from BM18, but not only. So if you are not familiar with tomography, I always try to remind people that tomography is not necessarily a non-destructive technique. Tomography means that you study the structure, internal structure of a sample on slices. They can be physical slices. So this picture is a tomography of a sausage. But if you do that with X-rays, with neutrons, or with MRI or other techniques, you can do non-destructive tomography. So 3D imaging without cutting the sample. And it is the kind of things I will show after, the X-ray microtomography. So I will explain very rapidly how it works. The microtomography, or the tomography in general with X-rays or with neutrons, is based on radiography. So it means it's based on projection picture of the sample. You have a beam that goes through the sample, and then you will record the picture after the sample with a 2D detector or with 1D detector, it depends. But the thing is, if you do just projection, the two samples that you can see on this slide, these two samples will give you exactly the same radiograph, because it's just a projection, so you are losing the second direction. The principle of tomography is, if you have only the radiographs, how can you recover the structure of the sample? So if with these two samples, you take two different radiographs with two different angles, then one of them is the same, but the second one is different. You can see that the internal structure there, the projection is different. And the principle of tomography is to use the information from the radiographs to reconstruct the slices. And to do that, you back project the information from the radiograph. And by doing that just with two angles, it's clearly not enough. You need much more to reconstruct the slice. So to show you how it works, here is an example. It's a quite old example. I think I made that in 2005 on ID19 at the ESRF. This sample, it's a piece of amber, so it's fossil tree resin, and inside you have a fossil plant that is mineralized with pyrite, so it's very dense. So when you do tomography, you do radiographs in 2 dimensions. And for each of these radiographs, if you take a single line of the detector, you can make a new picture that is called a sinogram. This sinogram, it is all the information to reconstruct one slice. Each line of the radiograph will become one slice at the end in the reconstructed volume. So this picture has a sinus curve shape because you have a rotating structure in the front of the beam. And by back projecting all the information from the sinogram, you can reconstruct one slice. So here you can see the red line is moving, and it's back projecting each angle on the slice. And you can see the slice reconstructing progressively. So this one, it is the basic principle of filtered back projection. That is the most commonly used algorithm for reconstruction. There are many other ones, but this one is the most commonly used. And it shows nicely how the system works to go from projection to slices. And then if you do that for any single line of the detector, what you have is a stack of slices. So you reach the third dimension of your sample. Each line of the detector became one slice. And so you can start, when you move in the stack, you can start to perceive the third dimension. And the next step after that is to go in 3D analysis, segmentation, quantification, whatever. You can do many, many things with such kind of data. So here is the result of the segmentation of the stack you just saw. And inside this amber piece, you have plenty of fossil insects, some arachnids also, myriapods, and so on. So this principle works for synchrotron, laboratory source, neutrons tomography, so plenty of things. But why are we using synchrotron to do microtomography? You have to know that most of the microtomography experiments are done with laboratory machines, the vast majority of them. Still, most of the synchrotron sources do have imaging beamlines to do microtomography because there are very specific aspects linked to these sources. The first one is as you have a lot of flux, you can use monochromatic beam. If you use monochromatic beam for tomography, it means that you can do exact reconstruction and you can be quantitative for density, assuming that you know the chemical composition of your sample. The second thing is, in a synchrotron, you are using a parallel beam geometry. As I said, you have the high flux, and also you have the partial coherence. It means the source is very small angular size. And because of that, in addition to just the absorption of the X-rays, that is the normal contrast system for laboratory machines, for instance. So you have the X-rays going through the sample, and if it is thicker or denser, it absorbs more. And what you have is a shadow picture. It is the principle of the radiograph. But if you have a partial coherence, you can also use other techniques based on phase contrast and not only on absorption contrast. On top of that, the synchrotron has much higher flux. It means you can do much faster scans than what you would do with lab sources, and you can also reach much higher resolution. One of the big differences between a synchrotron beamline for microtomography and a lab source, it is the geometry of the beam. On a synchrotron beamline, you are very far from the source. So you can consider that you are using parallel beam geometry to make the radiograph of your sample. And because of that, the resolution of the picture you do is limited only by the detector and not by the source. It's very different when you are dealing with a laboratory source, because in this case, you have a focal spot, and the resolution will depend on both the size of the focal spot and the divergence of the beam. So the thing is, if you want to have very high resolution with a laboratory machine, it means that the focal spot has to be very small. And because of that, you cannot have high power in the focal spot. So it's a trade-off between the power you can have and the resolution you can reach when you are with this conical geometry. In addition, it is possible to make conical geometry tomography with synchrotron beam, typically by using nano-focusing, and it is the base of the nanotomography, but I will not present this technique today. I will stay only in the microtomography. So one of the main points that was, let's say, one of the most important reasons to use a synchrotron some decades ago to do tomography was the monochromatic beam. Because when you have monochromatic beam, the absorption map you do through the sample is exact. If you are using polychromatic beams, the different energies will be absorbed in different way by the sample, and it will lead to an energy shift in the picture you record compared to the incoming beam. This effect is called the beam hardening, and for a long time, it was the main reason to go for synchrotron tomography. So this example is extremely old. I made that in 2000, if I remember well. So it's really what you can do today is much, much better than that. But it's a good illustration of what the beam hardening is. So it's a fossil molar of ancestor of orangutan. And on the right, you can see a monochromatic scan done on ID19 without any beam hardening. And on the left, it is the same tooth image with a laboratory machine without any filter and without any correction for beam hardening. So trust me, today, any lab machine can do even better than this monochromatic scan. But still, it's a good example of what beam hardening is. So the beam hardening, this energy shift will make false denser values around the sample and will create false structure. You can see here you have the feeling that the border of the tooth is straight, but in fact it's not. And it's because of the beam hardening effect. So for small objects, rather small objects, most of the laboratory machine can now work without any visible beam hardening, thanks to better source, to better filtering, but also to algorithmic reconstruction. Nevertheless, when you go to large objects that are quite absorbing, the beam hardening is still one of the main problems of the laboratory sources. Nevertheless, using monochromatic beam, even if it was the main reason at the beginning, it really changed a lot because, sorry, I forgot to show this one, to show the beam hardening effect. What you have there is the spectrum of a laboratory source before the sample. So you can see the Bremsstrahlung plus the fluorescence peaks of the tungsten source. If you go through 10 millimeters of aluminum, then you can see that all the low energies are completely absorbed, not the high energies, and so the average energy shifts quite a lot So in this case, 48% of beam hardening. It is this effect that creates the artifact I just showed. But the thing is, for a long time, monochromatic beam was one of the main points, but it's not anymore the case, because it turned out that if you are using a high enough energy with good filtering of the beam, and that you can reach enough transmission through the sample, so typically 20%, then the beam hardening effect becomes nearly negligible. That's why many laboratory sources can reach very good quality, but it's also true with the synchrotron. So if you want to be really quantitative on something, then you go for monochromatic. But if you want to have just very high quality data or fast scan or use of phase contrast and so on, then polychromatic beam is good enough to do that. And often it's even better than the monochromatic beam because you have more power, you have a much more stable beam because you have no monochromator. So you just have filters. You have the highest possible transversal coherence because you have nothing to degrade the quality of the beam profile. And you can reach much higher energies than with monochromatic. So during the last 15 years at the ESRF, most of the beamlines that we are doing only monochromatic moved to polychromatic for the tomography. So, and to show you that it is bringing better quality, on the top row, you have monochromatic scan of a fossil tooth done at 51 kiloelectron volts, and the same done with polychromatic at 68 kiloelectron volts average energy. So if you zoom in, you can see that the quality is better with the polychromatic. And on top of that, the monochromatic scan took 12 hours and the polychromatic scan took 2 hours. It's a very old example. It was done in 2008. No, sorry, this one was done in 2012. The same scan today would take 10 minutes with 4 times higher resolution, just to tell that things continue to evolve. But clearly, we would not do it in monochromatic anymore. Another example on much larger object, so this one is nearly 20 centimeters. What we did on ID17 in monochromatic at 160 kiloelectron volts, and what we did in polychromatic on BM5 at 140 kiloelectron volts average energy. Basically, you have the same quality, except that the first one was done in 2 days and the second one was done in 12 hours. So then I will move to what I consider to be the most important aspect today for the synchrotron microtomography. Why there are so many experiments done with synchrotrons with tomography. And this technique is the propagation phase contrast. In addition to the absorption contrast, the one I showed so far, if you have a very small angular source size and you are far, so it means the source is small or is far from the sample or both, then you have a partially coherent wavefront of X-rays that goes through the sample. And in addition to the absorption of the X-rays, the sample will also distort the wavefront. And this distortion will create interferential pattern. And these interferences, to detect them, you have different techniques. You can do interferometry, you can do DEI, you can do speckle tracking, whatever. But the easiest solution is just to use propagation phase contrast. It means you increase the distance between the sample and the detector, and just increasing this distance will make the fringes visible. So again, an old example done on ID19 at 5 microns, 25 kiloelectron volts. It's again the same amber blocks than before. In absorption, trust me, there are 2 fossils in this picture, but in absorption contrast, you cannot see them. If you increase the propagation distance by 1 meter, then you have the propagation phase contrast effect that reveals all the interfaces with these fringes. And this one increases the sensitivity typically by 1,000 times. So this effect is one of the main reasons to use a synchrotron today for microtomography. So as I said, it's an old example. It was an example in projection only, so just a radiograph. But you can do that in tomography. And here is another example. It's a fossil small egg from Thailand that is 120 million years old. Here is a slice made with conventional microtomography in absorption mode. The same done on ID19 in absorption. So you can see the quality is better because you have more flux. You can see some of the bones, but it's very difficult to see. And the same with propagation phase contrast. Same detector, exactly same parameters except 1 meter of propagation. And all these black structures are fossil bones. So basically, you have a complete skeleton preserved in this fossil egg. And if you look at what you can reach in 3 dimensions with segmentation, this one is laboratory machine, this one is synchrotron in absorption, and this one is synchrotron with phase contrast. So this example is from 2009. trust me, we can do really much better. So what I showed is just the propagation effect. So it means you see very well the border of the sample, the interfaces, but it makes the segmentation very difficult because you lose the differential contrast. So that's why it's important to be able to make the phase retrieval. Phase retrieval means you go from the fringes that are the second derivative of the phase itself, and phase is linked to electronic density, and you want to go back to the phase itself. So there are plenty of ways to do that. One of the oldest one is the holotomography that was developed by PHotons, if I remember well, in 1997. You take several distances of the same object with different propagations in monochromatic, and by combining these distances with a phase retrieval approach, you can do holotomographic reconstruction. On a real sample, here you have absorption in a very small fossil. Sorry, I'm showing a lot of fossils for the example because I used to be paleontologist, if you did not understood this point already. So this one is a very old fossil, 420 million years old. And you have a slice at 1 micron pixel size done in absorption. So the detector is just after the sample. You see barely something there. That is a fossil plant. Then first propagation distance, 100 millimeters. You can see much better the structure of the plant with the cellular structure. Again, if you continue to increase 300 millimeters, you see it very well. And this one is the phase retrieval when you combine the three different positions. And you can see that the contrast is much, much better. So if you look a bit closer, this one is the absorption. This one is the first propagation distance, the second propagation distance, and the holotomographic reconstruction. So for nearly a decade, this approach was clearly the most powerful one to study difficult samples, including fossils, but it was done mostly originally for biology. Then another technique came. It took some time to really spread in the different synchrotron beamline, but nowadays it basically replaced the holotomography because it's much faster, much easier, and can be done in polychromatic with much more relaxed conditions. This one is just single distance phase retrieval. It's based on an algorithm from Paganin and collaborators, but from this algorithm, there are plenty of different variations. So to show you what you can reach, this one is a modern tooth image in absorption, the same one with 1 meter of propagation, again in edge detection, and the effect of the phase retrieval with this algorithm. If you compare the three different pictures, you can see that the phase retrieval with this algorithm gives basically the same information than the absorption, but with much higher signal-to-noise ratio. So you can see much more details with this approach. If you do that in high resolution, this one is absorption, this one is single distance phase retrieval, and if you use false color, you can see that with exactly the same scanning parameters, except the propagation distance and the phase retrieval, the signal-to-noise ratio you can reach thanks to the phase is much, much higher than what you can do with absorption. So now let's move. All these examples are quite old. I will move to the more recent aspect and to the real challenge of propagation phase contrast. The thing is, if you want to image large objects with high contrast, because many things goes in the bad direction when you increase the size of the sample. You have to know that when you want to have stronger propagation phase contrast, you have different ways to do that. You can increase the distance between the sample and the detector. You can have higher resolution detector, or you can decrease the energy. But if you want to image large objects, you cannot decrease the energy. You have to increase the energy, so you will lose coherence. You cannot increase the resolution detector because you would lose field of view. So you have to increase the sample, the distance between the sample and the detector. But for that, you need to have enough coherence in your beam. If the coherence level is not enough, and you increase the distance, the propagation distance, what you have is blurring instead of having stronger contrast. So it means you are losing the contrast instead of increasing it. So the way to do that is you have to increase the coherence. And to increase the coherence, you need to have a smaller source size. Or you can also work at lower energy. But as I said, using lower energy is not really useful. So you can reduce, you have to reduce the angular source size. It means you can have a smaller source, and you can increase the distance between the source and the sample. That's why some of the synchrotron beamlines are very long. It is one of the reasons for the length. It is to have enough coherence. So you can see that when you want to image large specimens at high energy, it's a worst case because you are losing the contrast and you are losing the coherence. So you cannot have worse than that. And so the solution, if you want to go like that, is to make a very long beamline, such as BM18. BM18 is 220 meters long, and to have a very small X-ray source. So BM18 has been built with the new source at the ESRF, the EBS. And with the new lattice, most of the beamlines for large objects imaging were based on wigglers. And the wiggler sources, the size of the source does not change with the EBS. The EBS change a lot for bending magnet and for the ondulators, but not for the wigglers. But we wanted to have a beamline with large beam, high energy, and very small source. And that's why BM18 has been built on one of the bending magnet port, because here you have the beta function of the new lattice. And BM18 is built where you have the smallest possible electron beam, and so the smallest possible X-ray source. And on top of that, the source of BM18 is a very short one. It's only 11 centimeters in length, but it reaches 1.56 Tesla. It means that we have the smallest possible X-ray source at the ESRF with the longest propagation distance. We have the longest beamline. So when you combine the two things, you have the highest level of transversal beam coherence for imaging in the world. So this beamline, the concept of BM18 would have been impossible with the previous machine of the ESRF, because the coherence would have been limited by the source size. But with this one, we can reach a level of coherence that is really incredible. And that's why the experimental H is 45 meters long, because we can go to 36 meters of propagation. Basically, the coherence of the beamline is so good that when working at 20 microns, we could go to half a kilometer of propagation before having any blurring. But it's just, at some point, it costs a lot to make a beamline. 45 meters was already expensive, and after we have a road and even a river, so you cannot go to 500 meters. But let's say it would have been possible. So just few numbers to give you how it evolved compared to the example I showed you before. All the things I showed for paleontology on ID19, it was blocked at 60 kilo-electron volts. On ID17, it was possible to go to 160 kilo-electron volts, but each scan was taking days, and the propagation distance was limited to 5 meters. On BM18, we can reach 330 kilo-electron volts. The beamline is 220 meters long. We can go to 36 meters of propagation, and the sample can reach 2.4 meters by 300 kilograms. So everything has been done to do very large objects, but also to be able to reach higher resolution in the large objects. And it's a beamline that is done for propagation phase contrast, as you understood, but also for multi-resolution. It means in a large object, we can zoom in and go to see the details. So we are covering many different topics. In fact, the microtomography with synchrotrons covers nearly everything you can imagine where 3D imaging could be interesting. So it can cover biomedical, natural and cultural heritage, including paleontology, material sciences. We have a lot of industrial applications. We have geology, but we have also natural sciences and so on. So it's really everything where you can imagine that the 3D could be interesting is basically scanned with synchrotrons. So the three main reasons to build BM18, from what we understood, the high coherence. So I will show you the difference, what it means. The top picture, we are at 160 kilo-electron volts, so very high energy. The top pictures show you what would have been feasible with a beamline like ID17. So you have nearly no phase contrast when you are at very high energy, and you cannot go much further because it would become blurred. Below, you have one of the pictures done on BM18 with 16 meters of propagation, where you have strong phase contrast because of the coherence properties. Then the second reason for the concept of this beamline is based on multi-resolution. So multi-resolution, you start with the complete object. So in this case, we are at 40 microns. It's a composite T-bracket from aeronautics, and it should be free of defects. But in fact, when you do the tomography, you see bubbles everywhere. So we started at 40 microns, and then without dismantling the sample, without cutting, just changing the detectors and the beam properties, we zoom in and we go to 9 microns, and we go to 4 microns, and we go to 2 microns. And on this one, we went down 0.65 microns. That is the highest resolution we can do. So it's a pixel size, it's not really the resolution. And at this high resolution, you can see even the glass fibers in the resin composite, in addition to the defects. So all that is the second reason why we made BM18. It's a very old example. We did that only 1 month after the start of the beamline. So today we can do, we did the same kind of experiment on a sample that is 2 meters. This one was only 5 centimeters. Then the third reason is the high energy. As I said, we can reach 330 kilo-electron volts of average energy. So here you have, again, one of the old examples done during the first months of the beamline. On the left, it is a watch that was imaged by Fraunhofer on their high-energy laboratory tomograph. On the right, so 12 hours of scanning. On the right, it is the same one scanned on BM18 at 225 kilo-electron volts in 12 minutes. So it's a good reason why also to use such kind of beamline. And if you combine everything, so the propagation phase contrast, the multi-resolution, and the high energy, then you can do an interesting technique that we developed originally because of the COVID pandemic. So it's a kind of accident in research. It was not planned to work on that, but when the COVID crisis occurred, the EBS was just starting. We had just a few weeks to test the new source. It was not yet on BM18. It was still on BM5 at this moment. But we saw the very high level of coherence with the bending magnet beamlines on the EBS. And we decided to put all the techniques we knew for microtomography to make a single one, a kind of super technique, to be able to study the lungs of people who died from COVID. And the idea was to see the full anatomy of the lungs and then to zoom in down to the histological level to make the link between anatomy and histology. That was really a puzzling problem for the COVID thing. So this technique, the hierarchical phase contrast tomography, combines different approaches. First, the simple phase contrast, so single distance propagation. But as you can see, if you do that, you have nearly no contrast. Then you use the attenuation protocol, that is a way to normalize the absorption of the sample that was developed for paleontology originally. Then a technique to increase a lot the dynamic range of the detector. Then you have a lot of signal to noise. And finally, a system that makes possible the multi-resolution. So you can go from 20 microns down to 2 microns in a routine way. So here we are in a kidney and you can see the glomerular structure and so on. So, and to show that it was really a powerful technique, here on the top line, you have the picture from the synchrotron. On the bottom line, you have the picture from the same organ that has been cut and imaged with a microscope. So with the normal histology. And you can see a nearly perfect match between the two pictures. Okay, and then, as I said, it started on BM5. And 2 years after, BM18 was ready. And you can see the difference. On the left, you have MRI. On the middle, you have BM5, where so the original quality we were able to do with the HIP-CT. And on the right, with the same detector on the same brain, you have the BM18 result. So for BM5, you have 3.5 meters of propagation. For BM18, you have 31 meters of propagation. And here you can really see the effect of the propagation phase contrast. So why we use so much this technique? Because the sensitivity is much, much higher. The scan was also faster and the dose even lower. But the thing is, just have a look to the level of details you can reach thanks to the propagation phase contrast. So if you ask yourself, it's not feasible in vivo, unfortunately, the dose would kill anybody in less than 1 second. So this one was really unexpected, this biomedical imaging, but let's say it was a huge accelerator for BM18 because this technique developed for biomedical has been reused for all the other thematics, including geology, including industry, metallurgy, or whatever. And as I said, we started with quite small objects. So most of the synchrotron beamline in the world are working on samples that are typically 1 or 2 centimeters maximum. For a long time, ESRF was working on much larger objects, up to 30 centimeters by 50 centimeters, so with small tomograph. And on BM18, we just finished the big tomograph that can take 2.4 meters and 300 kilograms. And it started to make real scan beginning of end of last year. So here you can see the small tomograph and the big one behind. This one is a violin, this one is a cello. And in the meantime, we started with the violin with a small tomograph, and just 1 month ago, we made a complete double bass that is 2 meters tall. And with that, I'm done. So I hope that it was interesting enough.